Hello and welcome to Identity Office Hours. I'm your host, Mike Schwartz, founder of Glue. Today is episode 146. As you can see, I think this is one of the first episodes I've done not in my office. I'm at WeWork and in Austin, downtown Austin today. So happy to be here. Please, just a reminder if you want to help support the podcast, please follow it on LinkedIn. That really does help us get the word out. Our guests today are Amina Torlak, Senior Principal Applied Scientist at Amazon, and Rohit Kar, former PM at Google Cloud IAM, returning Identity guest probably like 4 or 5 times now. Welcome, guys.
Hi, thank you, Mike. It is my pleasure to be here.
Rohit, you're on mute now? No, we're not hearing you.
We're not hearing you. I think he's on mute.
Yeah, I kept it on mute because I was also playing our live streams right now on LinkedIn and on YouTube to make sure we're keeping track of comments. Thank you for the intro. Welcome this morning.
Great. Okay. Well, Amina, this is your first time. Actually, I'm going to point everyone back to Rohit's original appearance on episode 19 on continuous authorization. So if you want to hear Rohit's illustrious career trajectory, go back to episode 19. But Amina, you've never been on the show, so maybe you could tell us a little bit about your background.
All right, the backstory. So my expertise is in programming languages and formal methods, so specifically satisfiability solving, automated theorem proving, interactive theorem proving, and applying these techniques to program verification and program synthesis problems. Before I joined Amazon, I was a professor at the University of Washington, where I built a programming language that allowed people who are not experts in formal methods to actually build scalable verification tools for various domains. So we have applied that to verify control software of a radiation therapy machine at the University of Washington, to verify just-in-time compilers that are part of the Linux kernel for the eBPF language. Before coming to UW, my running joke is I did just about every job you can do with a computer science PhD. After I graduated from MIT, I went to IBM Research, spent some time there, did some fun stuff. I went to a startup. After that, I went and worked as a research engineer at Berkeley. So ended up at UW, and after UW, now I'm at Amazon.
Oh, that's fascinating. eBPF is I think the most important technology that people have never heard of.
Yes.
Actually, I'd like to pause right there and ask you as an intro on something people should hear more about. You talk about safety, formal methods, verification, and radiation. And I'm wondering if you could just give us your good old student tri-pitch on the Therac incident and how software has real consequences we've known for a long time. But I suspect you should teach better than I.
Oh, yeah. So I think one of the most infamous incidents that inspired a lot of the subsequent work on verification was the Therac 25 incident, where due to various concurrency issues, this radiation therapy machine accidentally over-irradiated a lot of patients and caused a lot of horrific injuries. So from then on, these really important systems, embedded system in radiation therapy machines, within aviation especially, have heavily used various forms of formal methods to actually verify that software is free of critical issues. So the thing that you have to be very careful when you talk about verification is you can never ever say that it's free of bugs. That's a meaningless statement, right? The only thing that we can verify is that there's some end-to-end property of the system that you care about that we have mathematically proven that the property holds. So to give you an example, for this radiation therapy machine software that we worked on, the end-to-end property was that if the machine went out of alignment for whatever reason during treatment of a patient, it would shut off. Because that was the key safety property. If any of the 400 knobs that have to be turned to put the patient in alignment on this machine went out of alignment for whatever reason, the control software ensured that the machine would shut down so they wouldn't be over-irradiated.
400 knobs? I mean, where do they get Amazon Web Services engineers to write this UI and drill out this control panel? I mean, I guess at least 401 knobs were the guys. No, the Therac story, and I hate to dwell on this, but it's a good intro for today's session. And I'm skipping ahead to top 5 takeaways of why Cedar is important. I came up for, wearing the UW shirt from UC Irvine. Nancy Levison wrote one of the classic papers on this incident in the early 80s, and that software can kill people.
Absolutely.
If you fix the software, you don't save people. It doesn't cure cancer. In fact, you might still have the question of there's still an electrical fault and the software at least isn't commanding it, but something else can go wrong. And so one of these, we'll come back later on to some of the classic reasons why at one level, formal verification of systems has remained a bit of a holy grail or just always right out of sight. But that means that we get inured as a field to think about how much great stuff we can do right now to make the world a better place. And if we're not dealing with quite human lives, we are dealing with cybersecurity. And especially in the world we live in, this stuff is getting higher and higher stakes all the time. So let's get back to diving into this and why maybe we should pay attention to not just developer velocity and whether the AI can vibe code security, and think a little bit about how we can make sure the security is something we can build our society on top of.
Absolutely.
It's actually an interesting point. It's a great use case. I hadn't heard it before, and it made me think about this trend in cloud computing to declarative syntax, where we're going to declare things that are true. And so this idea seems to align very well with declarative security, where we're going to declare this thing, we're never going to irradiate more than this amount. Amina, do you think that that's one of the major trends that we're trying to achieve, is how to move to declarative security?
I think so. At least that's where, things have been going over the last few years. And I think that is the right trend to, and the reason effectively is that, even if you put formal methods aside, we as a society have gotten really good. If you really think about it, like think about how many millions of lines of code exist and get executed every day and do amazing things for you. We have actually gotten really good at writing code and making sure that it does the right thing most of the time, that it's safe and so on. So the more of the tasks that we have to accomplish, like reasoning about authorization, reasoning about infrastructure, the more of those things that we can put in code, the more we give ourselves the opportunity to apply all the skills and tools and technique that we have developed for reasoning about other kinds of software to reasoning about these new kinds of artifacts.
And it's one of the themes. Yesterday I was at a SailPoint conference here in Austin. They host a great conference every year, Navigate. And we were talking about how if the trend is going to be to use generative AI to generate code, that we can't use generative AI to also check that code. That we need something that's more deterministic or trustable. And the one thing Gen AI is not is I don't really trust it to be right. I trust it to make me more productive, but I don't necessarily trust it to be right. We've sort of got off topic here, but any thoughts about that, about the code, how if we're moving towards this code world, is an analyzable security language part of one of the controls we need to make sure that we're safe?
Oh, absolutely. So I think this, what I just said, is going to be even more important in this new world, where it's not just going to be just people writing code, but people writing code with assistance from these tools that are, inherently probabilistic, you basically have to check their work. So to give you a concrete example, people internally within AWS have been playing with getting LLMs to generate Cedar policies. And it turns out, and it turns out that they can, do sort of a decent job directly from an English spec, but they become really good and actually give you the thing that you want if you use the Cedar type checker, you give them the schema, and you use the analyzer. Because if you don't use the analyzer, it turns out that LLMs are really sneaky. They're going to cheat. They're going to give you a policy that basically allows everything.
They make up features.
They do, exactly. So having these guardrails, type systems, which is actually a form of formal methods, right? So having type system, having analyses, all these things are going to provide guardrails that we can use to make sure that they do the right thing in places that matter.
I was going to start on asking about the design or the origins of the group. But Rohit, maybe before we go into that topic, did you want to have any questions or thoughts?
No, I think that's actually, I wanted to step back. I was immediately jotting down some later questions or thoughts about details of how Cedar works. But let's step back and ask why Cedar exists, right? The question of being a faculty member, at such illustrious places, and then suddenly getting a call from Amazon saying, hey, we think this. You're going to ask them, like, you don't build airplanes, you fly them. You don't build X-ray machines, but you do seem to deliver them overnight. Why do you need someone like me? And how does that journey begin? And how did the language history here begin? Because someone who's also studying the history of programming languages, there's a lot of genre and styles. So take us back a little bit, and also remembering some of our audience may need to be reminded, kind of what Cedar's good for. So, how did we end up with the park? So please.
All right. So that's to kind of give you the full story. So I was at Europe. I was working on this programming language. We had success applying it to real systems. It was super exciting, and I went to sabbatical, and then I spent the whole year writing code, and that's a luxury that you do not get as a professor. And after a year of writing code, I'm like, oh my God, I really miss this. I want to go back to doing this. And at the end of that year,
because as CEO of Glue, I also rarely get to write code.
Exactly.
And that's the reason I started the company, because I do love coding. But
exactly.
I totally empathize with what you're saying.
So at the end of that year, Neha Rungta, whom you had on the podcast a few weeks earlier, she contacted me and she said, "Hey, we need somebody to design a verifiable language for us at Amazon. Do you want to come?" And I'm like, "Wow, sure. I want to give it a try." And I joined in summer of 2021, and I started working with her and Darren McAdams. He's great. If you haven't had him on the podcast yet, I highly recommend it. So I learned. I didn't know anything about authorization when I joined. So I started reading papers, started talking to Darren, to customers, what the problem is, what are the pain points, what do we want to accomplish with this language? So I designed the first version and I prototyped it in Racket. So for those of you who don't know what Racket is a Lisp. So it is a language with a lot of parentheses. It is a beautiful, very well designed language, really good for prototyping fast. And we showed that prototype to people and they liked it. And that's how we ended up hiring the amazing Cedar team, which you see today. And, they built the real version of the language in Rust.
I mean, what kind of executive feedback do you get at a design review of, like, Racket, nice prototype, parentheses, the weapons of an earlier, more elegant age. But can you do it with angle brackets so we can make it look more like XML and more compatible with our YAML stack with some semicolons? Can you put some semicolons in? How did people react to the reviews as you started realizing, oh, I'm not talking to fellow academics anymore. There's someone at Amazon in the chain who cares.
I hid the parentheses. So the implementation had lots of parentheses in it, but the actual code that I was showing, it was just pretty much the Cedar syntax that you see today. And it's actually a really funny thing that you talk about semicolons. So here's a fun fact that you may not know about Cedar. You know how Cedar policies, they end with a semicolon? Mm-hmm. That semicolon is actually not necessary at all. So we don't need it for disambiguation, for parsing. The reason why we need it is that a lot of security issues come from languages that if you parse them and you can't tell that the parse has ended because there is no end marker, and a policy gets cut off and it looks complete, you can still parse it. You could parse something that says allow and actually should have denied. So this is why we have the semicolon at the end of the policy.
Human affordance that programmers need to see a semicolon before they'll pause rather than just keep going and interrupt the speaker.
Exactly. The parser actually doesn't need it. There's no ambiguity in the grammar, but we need it for the humans.
I mean, that's the thing I was worried about. You were telling some background compatibility story. At one point, the parser needed it, but then you didn't, and you can't take it out because at Amazon, things are famously kept around forever.
They are, but that was not the reason.
What else about the parsing made it interesting, or about the language structure was novel? And I don't mean for us to drop into an academic context, but I mean, you had to have also looked at some existing practices. Unfortunately, the history of access control languages is long. The history of access control languages that have made it into reasonable programming languages with IDE support and so on is very, very short.
Mhm.
Do you recall things that you look at, or even now look at as peers or precedents?
Absolutely. So, we looked at a lot of the previous languages. Like the obvious one is XAML. I still don't know how to pronounce it. Starts with an X. XAML.
Extensible access control markup language.
As a non-native speaker, there are many, many words that I can write and
I think it's
recognize,
now
but not
pronounced
necessarily pronounce.
for our readership or viewership, it's now pronounced alpha on behalf of David Broussard.
Okay.
It's not pronounced, again, it's the simplified language, but if you've seen it, XACML, alpha, absolutely. But there's not much precedent. Please continue. What did you think
Yes.
of those?
And that's the number one question I get, by the way, is how does Cedar compare to OPA or
Absolutely.
OpenFBA?
We looked at OPA. We looked at, of course, IAM, the AWS IAM, and we looked at Zanzibar, which was the authorization system that was built by Google, and they wrote a really nice paper and inspired a lot of startups. So we looked at those things, and if you think about it, Cedar takes inspiration from all of those things. Like many authorization languages that you see today have the PARC format. That's what we call it, which is principal, action, resource, context. And it's really answering this question of, can this principal perform this action on this resource in this context? So Cedar follows that because, it's familiar, it makes sense, it's a good mental model. It has the allow and deny syntax and semantics. And we had one of the more interesting discussions in the design of Cedar. It was debated endlessly. I can't even tell you how many hours we spent debating that. What happens when there is an error during evaluation? So we can't bail, right? So we have to give meaning to error, right? How should errors be treated? So Cedar chose to treat errors in the same way as AWS IAM, almost the same way, which is when a policy error, it is treated as false. So it's just skipped. Okay, and that is a choice that has worked well for IAM, but Cedar is not IAM. It aims to apply to a broader set of use cases. So the question was, if somebody wanted something different. So let's say that if a deny policy errors, they didn't want to treat it symmetrically. They wanted to treat it asymmetrically to a permit policy, right? Maybe enforce an error in deny. They could still do it based only on the output that we provide, not by changing the evaluator. And that caused, for example, one of the things that the Cedar evaluator does, in addition to returning deny or allow, it also tells you what errors, and it also tells you the set of policies that were responsible for the decision. From those two pieces of information, you can actually reconstruct any combination algorithm that you want for deciding whether the final outcome should be allow or denied, depending on the outcomes of the individual policies.
So it guarantees on deny that it's correctly denied, but it may not be able to tell you all the reasons why you were denied. But it guarantees if it's an error, here are all the statements that contributed to being unclear.
It will tell you. So it will collect. You will give it a set of policies. It will evaluate every single one of them. If any one of them erred, it will record that and give you back as a set. And the decision is going to be something either allowed or denied. And if it's allow, it will give you all the allow policies that evaluated to true. If it's denied, it's going to give you all the forbids that are evaluated to true. Or if there were no allows, well, you get the empty set. But from those two pieces of information, you can actually reconstruct not only the default behavior that we give you, which is skip on error. You could also do enforce on error if you wanted to.
And then those are the diagnostics, right?
Correct.
Yeah.
Well, I mean, to pull back, this is better than diagnostics. We talk about explainability in AI.
Yes.
So a lot of folks are on top of several different trends. And if you're following the technology conversations these days about artificial intelligence, one of the big problems is that LLMs are non-deterministic. Depending on the temperature, you might get a different answer. But the more profound one is that AIs can't honestly explain what they do. We use terminology like chain of thought or explain your steps. But chain of thought is just a chance for the LLM to bullshit you into believing this is the things I would have tried taking. It doesn't control how actually the outcome thing happened. Explainability at the rigorous level is one of the huge advantages here, and something I'd love to come back to perhaps as one of the candidates for our top 5 takeaways about why Cedar. But I was curious if you've had incidents where you've had to explain to colleagues or folks in the business, because in Seattle, there's a lot of different businesses, but what is different between AI as a breakthrough and AI for logic? Because this is kind of like the kinds of things involving chess, solving SAT solvers and Z3, some of the whole set of logic technologies and applied reasoning technologies are classical high tempo AI topics. They're just barely overshadowed by the amount of funding going into these statistical and language methods right now. So my question would be, how do you approach this definition? If people ask you, like, I don't know about these new systems, can they explain what they're doing? What explainability or transparency?
So that's actually a really good point. So it turned out that these diagnostics that we returned had more use cases than we originally thought. But when we were designing the language originally, the reason why we returned the diagnostics is because of the experience that people went ahead within AWS. And the engineers told us the most important thing is that we need to be able to understand why this is the authorization decision. You have to give us enough information to figure that out. And that's actually where the diagnostic part of Cedar came, of the Cedar output.
Guys, we better pivot into the top 5. So, when I talk about Cedar with customers, I always start with analyzability, and to me that was really like the one of the most important features. But maybe you could talk more about this property and how attainable it is, and where we are in terms of tooling to make it actually attainable and useful.
That's actually a really good question. So, in real life for a general purpose language, it is not attainable because, you will run into the halting problem and so on. Cedar is designed so that every policy in the language can be expressed as a formula in SMT, which stands for satisfiability modular theories, which is the input for these solvers, which are automated theorem improvers that we're using to reason about the semantics of Cedar formulas. Now, just reducing something to logic is not enough, okay? You can reduce it and the solver still dies on it, right? So there are three properties that we maintain during this reduction that are important both theoretically and for practical performance of these analyses. So one of them is soundness, meaning that any tool that's using this Cedar compiler from Cedar policies down to formulas is sound. So if we come back and tell you this cannot happen, we have found a proof that it cannot happen. So it's not going to miss anything. There are no false negatives. The other property that we ensure is completeness. And this is usually the property that you cannot ensure for a general purpose language. And that means that there are no false positives. If we find a violation of your property, we're going to come back and give you a concrete test case, okay, an input, a request, and an entity store, such that if you were to run your policies against that input, it would actually violate that property that we checked for you. And the final one is decidability. So there's this fragment, a subset of first order logic, for which it is possible to definitely decide, given enough time, which may be exponential time. In practice, it's a lot better, but it's definitely possible, given enough time, to decide whether a property holds or not. And that is actually not the case for most of first-order logic. So the thing that's really special about Cedar is that we hit all of these 3 properties that are really hard to achieve in real life, actually impossible for general purpose languages, and hard to achieve for DSL. So Cedar is very carefully constructed to hit all 3 of these points.
Could I ask you to repeat that in maybe a more grounded context? Tell them what you're going to tell them again. So a classic finding, an advantage that Amazon Web Services has for automated reasoning is no public unencrypted buckets.
Yes.
You might say, hey, this is a good obvious rule in our company. I can't think of any good reasons why. Let's make sure all of our S3 buckets are always, if they're ever going to be accessible to a public world or attached to a process that's going out there, they should be encrypted at rest somehow.
Mm-hmm.
And now there's a great little checkbox in the system that says I can do that. It doesn't mean I have access to all the language and all the guts, or those are the insiders, between Balsa and Zelkova and all the different things that might be going on to make it happen. But as an end user, I get a simple benefit that this is a
Yes.
provable property about the system. So in the case of Cedar, how might I walk through what soundness and decidability and so on mean for a rule I might be creating for my own book auction site? Like, okay, only the person who listed the book for sale can remove the book from the auction or end it early, or change the price. So how do things like soundness, decidability apply to those of us with more real world problems than running a hyperscale cloud?
Yeah. I mean, that's a very good question. So for the example that you gave, here's the property. Can you repeat the property again?
There are no public unencrypted buckets, or in this
Okay.
case, only the seller of a book can remove it from the auction.
Okay, only the seller of the book can remove it from the auction. Okay, so let's say that is a property that we're checking against your set of Cedar policies, and the tool comes back and says this property holds. So what does that mean? Because the tool is sound, it means that it holds for every possible request that could ever be issued, and for every possible state of your entity store that you could ever end up in. So really, soundness means proof that this property holds over all states and over all inputs.
And now where would in a complete system we bring up what informally people want it to do, which is be reasonable and be logical and realize, wait, some part of the system built on Cedar should tell you, you need the admin and owner of the website to still be able to delist the book of offensive content because we're not going to sell that sort of thing on our site. And you realize, yep, I correctly wrote my policy. Only the seller of the book can remove it. And you realize maybe that's not the wisest policy. That might come quite a bit layers up. Those are political and economic considerations. But how do you think about tools that have grown around this to help people write wise policies, which is different, wisdom being different than correctness?
Yes, so that is different, although a lot of, so my professional bias, right? Whenever I talk about analysis and so on, my mind will always go to verification. So that's kind of the classic use case for these SMT-based tools. That's actually not the only use case. There are many problems about reasoning about code, and policies are code, that are expressible in terms of these logical constraints that eventually are handed off to a SAT solver. So another classic example is actually program or policy synthesis, right? So we invert the problem. Instead of giving me the problem, the program, and asking me if the property is satisfied, you give me the property and say synthesize a program that satisfies this property. So a lot of the ability to translate a language to logical constraints is extremely powerful. You actually get way more than just property checking for free.
So, Mike, that's what I wanted to pick up on there too, is that the great thing about the Cedar ecosystem, you can do the reverse, which is to say at our book auction site, our hypothetical Amazon competitor built with Cedar as our IAM system. Yes, anyone can list a book for sale, but in some books I might need to be as an admin, go in and take it off sale, or some books might have a different price on them. But I also don't want to have a rule that says, interns, I just hired an intern. Interns can't look at books for sale in production. They can play with all the test code they want. And so here's a program synthesis problem. I want to make a statement like, interns can't sell books in production. That involves you tagging a bunch of things as prod versus test machines. It involves you deciding what interns are and putting them in the right group or analysis thing. And it involves maybe some logic that's like lock them out of this Dropbox or these S3 backups. How do you begin thinking about how people use Cedar in practice when they're trying to reason out security in multiple different systems or at multiple layers? I want to compile or synthesize a program that does this, that has an effect in multiple systems. But first off, is that even kind of program synthesis coming, or should we be expecting to use Amazon Q to just talk to it and say, hey, here's the policy I want, and it'll write the Amazon verified permissions for me?
I don't know if that's going to happen anytime soon, but we're certainly heading in that direction where in kind of the technical jargon that people use for this is auto-formalization, which is specify something precisely enough in English, and then you will get a formal description of it in a language like Cedar, if you're talking about the authorization policies, or in a theorem prover, if you're talking about proving something about math. So people are doing that, and they're doing it successfully. Is all I can say at this point.
Mm-hmm. But then, the thing is, it doesn't help to set all the security integrations and gates absolutely correctly in my application. It's built on top of things below me, and it's built on directory services outside of me. And as you get to the classic bugaboo of formalization approaches through history, it's been thanks for proving an end-to-end property of one part of this overall human system.
Yes.
How does, how do you look at that problem, and where do you see some opportunities?
That's a good question. I mean, the thing that there's an important notion that we have in informal methods when we reason about complex system, which is the trusted computing base. It is not feasible or possible to reason about an entire system most of the time end to end, which means that there are parts of the system, components, which you trust to be correct. The thing that you have to do, though, is in order to make the behavior of those components a part of your formal arguments of correctness, you have to make assumptions about them. So the way that we deal with that in real life is when you make those assumptions, then we take extra steps to validate them, to actually provide evidence that those assumptions that we can't verify because it's not feasible. Maybe the component is written in C or TypeScript or who knows what, right? Mm-hmm. But you still have to validate that the assumptions hold, because otherwise, where you're going to get the guarantees. And you can do that through various means, like code reviews, testing, like all of the normal software practices. But yeah, whenever you're making any claims about correctness or proofs or end-to-end properties, you have to be very careful to state what your trusted computing base is and what your assumptions are. Because at the end of the day, what you prove is only as good as how realistic the assumptions are that you made about the world that you cannot formalize.
Well, it's a little worse than that. In the world we can't formalize, we've all been trained academically to think about these problems and always pay respect to them. But the problems are accidental in nature, or when systems interact poorly. But now we have adversaries, and adversaries can attack wherever they want and where they choose. And so just because we didn't choose to pay attention to locking down the whole system isn't where the cyber criminals are going to attack. Right. So the definition, too, is it's a constant issue. It's not our keeping up with the competition. It's keeping up with the adversaries. And,
that's right. That's right.
In one part, you may not have attention to another.
Yeah, if I could interject for a second, one of the challenges is, so we have this great new tool for doing analysis on policies, but there's another layer of tooling that you're alluding to that we might need to understand the interaction of all our components and to really govern, because govern means we understand, what are our capabilities and what are the risks, and I feel like we need a whole new level of tooling in order to move up from this new ability we have to analyze policies up into, how can we really effectively use this as an enterprise? Where do you think we are in that journey?
So, we're building something like that internally within Amazon for Cedar specifically. And it really comes down to asking questions that Rohit pointed out earlier, which is IAM has this thing called Zelkova, which is the compiler for IAM policies to SMT. But that thing by itself is not necessarily interesting. That's actually not what you interact with. What's interesting are the properties built on top of it, like no external access to my S3 buckets, or the new analysis that was launched, which is, tell me the internal access patterns that are happening within my account. So the same questions become relevant to Cedar. So what are the actual generic properties that we should be checking about policies that people care about? So, from the interactions that we had with teams within Amazon, and there are many, many teams using Cedar, there are some properties that are interesting for the kinds of things that they are building. And those are the properties that we're focusing on checking initially. And, as more people use this analysis, the more we're going to learn about refine our understanding of what it is that people really want to know about their policies. One thing that often comes up is, policies in some sense are very compact, very abstract representation of what can be done. Human beings are actually not that great at reasoning about abstractions. At the end of the day, often what people like to see is a graph, right? In which you have principles on one end, resources on the other end, and then edges between them, showing what action that principle can perform on those edges. And that's actually, for example, that's very useful for auditing, right? You can actually show that list to an auditor and say, hey, I have actually proven that only Mike and Rohit can access this resource, nobody else. I have a mathematical proof that this is true. And that's a very powerful thing that you can give to an auditor.
In fact, I was reminding viewers that it was just a few episodes ago in IOH 135 that we had Cedar Analysis Toolkit. And in fact, I'd love to hear a little more about that as a use case of its precedents and its uses. That's what gets the hardest thing that this language has among some others, which is the ability to answer what-if questions.
Yes.
Before I commit a change to the policy language, how many more people will get access to this item? If I have a problem or I have an error message or someone's being denied, can you tell me what are the statements most likely to have caused this problem, or where should I change the policies with the least impact? Is it I should give all engineers access to this backup, or just add this one intern to the intern groups?
Yes, exactly.
I actually wanted to make one other interesting point about the future state. So making policies, one of our previous guests, we had a conversation about digital rights. And so an asset like a photo, we might give you access to it, but that might come with obligations, for example, to display a photo credit, or also restrictions, never publish this photo in Russia. And Cedar, one of the interesting things about the analyzability is, does it let us sort of get more confidence about these future states than maybe other mechanisms of evaluating policies?
That's actually a good question. The analysis itself can certainly answer a question like, are your policies set up in such a way that there is no possible input? It doesn't matter whether it happened yesterday or today or tomorrow. There's just no possible input under which this particular property is violated. So for us to check that property, it has to be part of your authorization model. But if it's actually encoded in your policies that, for example, you can view this photo, but you cannot download it, that we can definitely prove that this is the case.
Interesting.
You can prove they don't have permission to do it. Proving that the entire system doesn't have a way to vend an S3 signed year old photo, that's the hard part.
Absolutely. We cannot reason. The only thing that we can reason about it's what's within your Cedar policy. So the content of your Cedar policies. Now, whether you're calling, if you forgot to call the authorizer, the Cedar analysis is not going to help you with that. You actually need another kind of analysis, like if you're calling Cedar for Java.
Is my code correctly relying on the Cedar embedded libraries or the Cedar code at the right places?
Absolutely, yes.
We've spent
you need different tools.
Love to see that.
We spent almost the whole time talking about analyzability, so much for getting to the top 5. Maybe we could just take a brief digression into expressiveness, because Amina, you said before we wanted to be able to express all the different types of access policies, especially RBAC, but I guess ABAC or potentially REBAC. Now that, with 2 years into Cedar or so, are you hitting any of the boundaries of expressibility? And so what's the real world feedback been on your expectations of it versus what you're seeing the struggles of the limits of it, let's say?
I mean, that's a great question, right? So whenever you are designing a language where analyzability is a goal, you have to play this game where you have to trade off analyzability and expressiveness. If it's too expressive, you can't analyze it. If it's not expressive enough, then it's not usable. So for Cedar, we carefully chose the construct so that you can express role-based access control pretty much anything that you would want to express ever in RBAC. Attribute-based access control, more limited. For example, you can't write a loop. And relation-based access control, it is expressible, but at this point, it does require some, legwork on your end, like correctly setting up the hierarchy and so on, so that you can express your relations as essentially set valued attributes. So it is expressible, but it's not as natural as, let's say Zanzibar, which was designed for exactly that. It handles only one thing and it does, relation-based access control. So Cedar has had to be more flexible than that. We wanted to encompass all three of them. And we are absolutely running into the limits of expressiveness because, once your language becomes popular, people get excited about it and they want to use it for things that it hasn't been designed for, right? So they will ask for features that, we have to come back and say, unfortunately, we can't implement that feature because if we did, the language would no longer be analyzed.
Like iteration, for example.
Exactly. So iteration is a classic example, but there is an exciting development there. So a classic ask is, can you give us a limited form of iteration? So for example, can you give us an operator that iterates over a set? So it's guaranteed to terminate, right? Like the sets in Cedar are bounded. So give us an operator that checks whether some predicate holds on at least one element of the set. So that's like the for any operator in IAM, or whether this predicate holds for all elements of the set. So that is the for all operator in IAM. Well, it turns out for the longest time we couldn't do it, right? Because it was not known whether this continued to be decidable or not. But like 2 months ago, a paper was published showing that there's an extended fragment of logic in which some form of these predicates actually are decidable. So, that is something that will eventually, from the science, from the publication, from it being pushed into the actual SMT software that you're using, will probably eventually make it into Cedar, some form of an operator that can iterate over a set and check whether the predicate holds for all or some elements in the set.
I think it's a really exciting place to close on. I see the birds, and I wanted to see if it would help for our listeners too to reiterate that story with more of a concrete example. I know it's somewhat fraught on the fly here, but
we'll do that. How about that's the last question, and then after that,
yeah,
we'll go
that's my question. Is like, can we repeat that? That's very exciting. But when we talk about iterators for any, like, so if those are, for instance, real-time authorization, continuous access evaluation protocol, we have these shared signals. Like I can log in, but it's a $50,000 loan. I want you to touch your second factor again, or I need to know that you're also from a company-issued laptop or an IP address in this VPN. And so here's a set of conditions that says, I need any of the following to be true. That is the IP address source, one of these IP addresses, is the transaction value below this transaction amount, is the machine that they're calling from have a key that says that they've been recently virus checked. Is that an example of this, or could you correct me and say, what do you mean is now decidable that might have been not in Cedar's decidability in 2025?
So what you're describing, we can express already. Yeah. So here's the thing that we cannot express that hopefully we'll be able to express maybe in 2026, but that is if you have a set of IP addresses,
yes,
is there at least one IP address in that set that is within given range?
That's right, because all of my bank branches have a different set of addresses, and I can't enumerate them always, but I want to say it's one of them.
Yes.
I have a good example too.
Yes.
I'm giving you a number of tokens from different issuers. Will one of these tokens satisfy the requirement?
Yes, that's another example where you would want this.
I've been personally struggling with that one.
Yes, it's tough.
I think Liana mentioned this potential of enhancement, but it's going to be sometime in the future.
Yes,
before
we'll
see it. As you mentioned, it's making its way through.
Exactly. It's like, but it's exciting. It's like, at the beginning of this year, we didn't even think it was possible. A few months later, paper comes out. The people who build the solver contact us, and we look at them and just like, wow, cool. We can actually productize this soon.
I'm excited about that feature personally. Actually, I wanted to, something I was saying yesterday at the conference to people when they were asking me, I don't want to present Cedar as a panacea. There is no silver bullet here. And it's not like, as you mentioned, graphs are very elegant at solving certain problems. If you look at the best way to do document sharing, it's probably a graph.
Yes.
And that's a good thing. We don't have one way to store data. We have lots of persistence mechanisms. We don't need one way to evaluate policies. But something that I've been advocating for is that because of Cedar's property of analyzability, whatever we can express in Cedar makes it analyzable, which makes it easy, which reduces the amount of manual steps we need in order to achieve our security objectives. And so, yes, we might have some patches of other things, but do you think that this is that what I'm saying is actually true? That as we move more to Cedar, we can create more automation and reduce the manual labor of auditing policies.
I do think that's absolutely true, and I also think that even despite my personal connection to Cedar, I completely agree with you that it's not a panacea, right? It's a language that is designed for this particular domain to make sure that we can reason about policies in this domain, that we can authorization domain, that we can analyze them. But the real world, there's no one language to rule them all, right? Like even when you're building a software system, you're not going to just use Java. You're going to use Java and Python somewhere else and TypeScript and whatnot. So in terms of system design, what Cedar gives you is, at least for this security critical part of your subsystem, there are certain guarantees that you can make, at least about the authorization policies that you're writing.
Like, don't irradiate the humans more than they can survive.
Exactly. But the way really to think about it, right? The way that I think about system safety, it's there's no single solution. You have to layer the solution. But really, what makes the problem tractable for the human mind is to be able to state something about a single component, right? And use that abstract model that's in your head to reason about the entire system. So what Cedar gives you is that when that component is your authorization policies, whatever you state about it, we can actually give you a mathematical proof. You don't have to rely on testing alone. There's nothing wrong about testing. For other components, you're going to do testing. But really, it's about automating the properties that you can check about a subcomponent of your system as much as we can.
I think we better go to last thoughts. Amina, we'll give you, or Rohit, why don't we'll give you last thoughts. That way we'll give Amina last thought.
Amina definitely deserves last thought, because as I was listening along, I thought mine was, I want to live in that world. That sounds like a great place to be, because where we live today is vibe security.
Yes.
Right?
Yes.
Does that subsystem seem critically secure? I've got a good vibe about it. So please have Cedar do better than vibes.
Thank you so much. I mean, I just my parting thoughts are, thank you for inviting me. It was such a fun and exciting conversation, and thank you for running this podcast. It's been a real service to the community to make people aware of what authorization is, and also the cool things that we can now do for your authorization policies that might not have been possible 20 years ago. Keep in mind that all of these technologies that sound like magic now, the solvers and the theorem provers, they're getting better and better and better. Cedar that you see today, the things that we can do would not have been possible 20 years ago. So it's a pretty exciting time to live in if you're in authorization, if you're in programming languages, and if you're in formal methods.
Mm-hmm.
Awesome. Well, so I just want to quickly mention, we only mentioned 2 of the candidates. So I'm going to mention the last 4 we didn't get to, and maybe we need 2 more episodes to cover them. But we didn't talk about ergonomics or ergonomic syntax, or basically human readability of the policies. We didn't talk, I guess we talked a little bit about safety, right? Maybe a safety and analyzability.
They're very closely related, actually. They're
Yeah.
2 sides of the same coin.
Performance. And the last one that was really key for me was portability, the ability to run Cedar in a database as a plugin, or in the browser, or in the cloud, that it's very small and compact. And that was actually the main, one of the drivers for us selecting Cedar. So next time we'll need more time to discuss So with that, I'll have to say thank you so much, Amina, for joining us. It's been a real honor. Thank you, Rohit, for helping me on this episode. You're welcome anytime to give me a break so I can think of a proper next question. Yeah, so thank you, audience, for tuning in whenever you're watching this, and we'll see you next time.
Thank you, Amina. Thank you.